So now if I look at plan A, the net present value of plan A is 740.3, right, based on the current demand configurations. The NPV of plan B is 45.8, right, based on the current configuration. All right, why is that? And each of you will get something different, right? Each of you will get something different. So for me, what has ended up happening is that year 3, well, for whatever so year 1 I manufactured 350. Year 2 I invested in the second plant, right, in the small plant, but I still didn't manufacture as much because the demand wasn't there. And in year 3 I invested in the third plant, but the variable operating costs, etc., seem to have been much higher. So overall plan B has performed very poorly for me. Oh, but these have here we are. The demand has been taken from that sheet, right? So the demand is taken from that sheet view. Okay, but my overall NPV is only 45.8. Oops. Or well, I seem to have hit another random and I get all other kinds of NPVs, right? So in some cases now I hit another RAN and the NPV of plan A and plan B are again very different. Okay, so I'm now able to randomize, but the problem is each of us now gets a different NPV A minus NPV B. Which ones is correct? Right? Is mine correct or yours correct? Right? And among you, which one of yours is correct? Right? So how do I solve this problem? Right? I wanted to have some randomized demand because I can't really predict it. I put in the randomization, but because I put in the randomization, does that make it, I get an answer, you get an answer? How do we actually resolve this? Maximum minimum values of what? Yeah, maximum minimum values of NPVs for? Yeah, but maximum minimum means I have only one value, right? I have A is 740, B is 40.3. I'm getting a difference of 700. Maybe you're getting a difference of 120 or 640 or whatever it is, right? So how do I deal with the fact that yes, I've been able to put in randomization, but the problem by putting in randomization is that we don't have a single source of truth, right? So here's where there's a technique that I don't know, maybe you guys have come across called Monte Carlo simulation. So Monte Carlo simulation says, don't do it once, it makes no sense. Do it 2000 times or some large number, do it 1000 times, 5000 times, whatever, and then average out those 5000s. That 5000 or those 2000 runs that you do, and that will give you a little bit of a measure of what is the expected difference in net present value. So if you go to the last sheet here, right, in some sense that's what has happened, right? So for plan B, what we've done is we've done the demand and whatever 2000 times, right? So it will go all the way up to 2008, right? Row number 2008, right? So I've got 2000 iterations of plan B, and so you see I've got a large number of net present values. But then what I've done is I've calculated the mean, right, of 2000, and I've also calculated a maximum and a minimum, right? And the idea is because I've done 2000 of these simulations and I assume that they're roughly normally distributed, this is probably a good expected value, right? So if demand does not vary, right, I had a particular NPV for B, right, which was I can't remember what it was, 156 or whatever. But if demand does vary, then the expected NPV for B is about, or the mean NPV is about 60, right, is what this is coming out. Okay, so this is now a bit more sophistication in terms of analysis because I now have randomized demand. Imagine we're trying to do this for a highway, right? Imagine I just took one set of traffic projections, right? There's no, and okay, I might do a little bit of sensitivity, but sensitivity is not randomness, right? Sensitivity is sort of purposefully saying what if demand was 2% higher, 3% higher. But now I'm randomizing demand. I'm randomizing demand and I'm looking at a number of scenarios of demand and then deciding, what would the average demand be. So we can do the same thing for A, and we can use the data table for that, right? So this, here, essentially I would say what I want to recalculate thousands of times is the NPV of plan A. So the NPV of plan A is what maybe I should make this bigger, huh? Okay, so the NPV of plan A is what I want to calculate a number of times. What do I want to vary? Yeah, I want to vary demand, right? But which cell do I want to vary? Yeah, but so earlier the question I'm asking is, earlier I wanted discount rate to vary, right? So I went in and put discount rate varies. Okay, so here what is actually varying? The random numbers actually vary, right? So in other words, I'm not varying any particular parameter, right? I just want to do this 2000 times, right? So what I'm going to do now is I'm going to select this whole table. Okay, there's probably a good way to do this, but I don't know how, so I'm just scrolling until I get to 2008. Got that. I've got 2000 cells selected, and right on top here I've got this, next to NPVA, right, I've got the value that I want to compute, right, which is the NPV of A. So that I need to vary, right, 2000 times. So I've selected 2000 cells, okay, but deliberately I'm not selecting, I'm not putting in any numbers. See, earlier I was varying my discount rate, I don't want to vary anything, I wanted to do it randomly. So I go back to the same thing, I do data, what if analysis, data table, alright, and in the column input cell, I just click a blank cell, right. So I'm saying, take, this variable which is nothing, right, and vary it 2000 times. Okay, so essentially I'm saying, okay, just sort of redo the whole thing 2000 times, and knowing that every time it does it, there'll be a different random number that comes in, there'll be a different demand distribution, and NPV of A will change. So once I say okay here, so for the benefit of people online, what happened was we had not put in the demand. So we need to go back to the Plan A web sheet, we need to click on demand, and I've got to say demand is equal to what I got from the random function. So this is the demand for year 1, this is the demand from year 2, and this is the demand from year 3. Correct? Now I should actually, if I go back to simulation, very nice. So I have a bunch of values that have come out. Okay, and I didn't have to stop the recording. Okay, wonderful. Okay, great. So does everyone have a series of random values for NPV A? Okay, so again, so what we've done is slightly just more sophisticated. We've said let's do some Monte Carlo modeling. Let's take demand. Let's see that demand varies. At the moment it varies normally around a mean, and let us then try to simulate and see if there is some variation, what would it be? And I've taken the demand as varying 50% around the mean. You can go and change that 50% value to 40%, 30%, right? So we can have all kinds of variances, right? You can also have all kinds of distributions, right? You can have a normal distribution, you can have a triangular distribution, whatever kind of distribution that you want. Essentially, as long as you can generate a random number, right, and you have some idea of the shape of the distribution, you can start sampling it, right, which is what we are doing, okay? And we are finding, and I'm going to find out the mean of this. So I'm saying the mean of this is going to be the average of essentially B9 to B 2008. Okay, so the average is 98.9. The maximum is going to be the maximum of B9 to B 2008, and the minimum is the minimum of B9 to B 2008. So I just use the max and the min functions. Just use the maximum and min functions, and you find, right? So roughly you find every time you click there's a slight variance, but roughly the mean seems to be close to 90, 100 in the case of NPV, in the case of Plan A, and it seems to be about 65.05 or whatever in the case of Plan B, okay, with varying minimum and maximum, okay. So are we all here at the moment? So far, are we all on the same page? Yeah, one by one, Harsh. So that is based on how do you decide uncertainty, that you sort of have to do some kind of analysis to figure out what is the kind of distribution you are seeing in the sample, what kind of distribution does it fit, what is the mean of that distribution, what is the standard deviation. The standard deviation or the variance is some measure of the uncertainty. Based on that, what do I put into the model, right? So that you have to do that data driven analysis to understand where that 50% comes from. Okay, yeah. The demand values are changing here, no? Every one of these simulations, the demands are different. So what matters here is the 300, 600, 900, because I am varying around those numbers, right? So that matters, but beyond that, every one of these 1000 that you're seeing in the yellow here is a different run, right? And it's completely different demand. So essentially I'm saying it's varying, right? Do you know how much traffic there'll be on the road tomorrow? I can't precisely tell you how much there will be. I probably have a range, I have some kind of a probabilistic view of what that traffic would be, right? But I can't tell you exactly. So the traffic could be at the lower end of that band, it could be in the higher end of that band. So I'm just sort of simulating it, right? The reason this is interesting is because of an inequality called the, or an equality, a relationship which is called the flaw of averages. And the explanation for the flaw of averages, goes like this. Just if you get 50% less demand, right, in year 1 and 50% more demand in year 2, on average you meet your demand, right? That's the law of averages, right? So I'm supposed to get 300 every year, right? I get 150 one year, I get 450 the second year. On average, I've still met my demand, right? I've still got 600 customers walking through my door. The problem is, think about the fact that you own a hotel, okay? Your hotel has 100 rooms. Okay, you expect 80 people to come in, right? Because this is good season, 80 people, you always have some buffer rooms, but there's a 50% probability of it going up or down, right? So on the one hand, if you get 40 people coming in, how much money will you make compared to what you expected, right? You expected 80 people to come in, only half of them are able to come, right? How much money do you make? Half of what you expected, right? Now the other scenario happens, 120 people come in. How much money do you make? Right? How much money do you make? How much money as a percentage of what you had in mind? Only 25% more, right? Because your rooms are capped at 100, right? 120 people came, but you couldn't service them, right? Because your rooms are capped at 100. So even though my demand was 80 and it varied uniformly 50% this way, 50% that way, when it varied 50% below, I lost 50%. When it varied 50% above, I gained only 25%, right? And therefore, the distribution, although the distribution of demand is symmetric, my ability to service it is not symmetric, right? And therefore, I'm losing more than I'm gaining, right? And that is actually happening here as well, right? Remember, in the first year, I've built, I have a capacity of 300. In all those situations where I get between 150 and 300, plan B is fine. In all those situations where I get between 300 and 450, I'm making money in plan A because I have 900 capacity, I can build all of that. I'm not making money in plan B because I only have one plant of 300, right? You guys understand the logic? Right? In year 2, I have 2 plants of plan B, so 600 units, right? But the demand varies between 300 and 900. The demand varies between 300 and 600, no problem. I service just as well as plan A, right? But the demand varies between 600, those situations out of these 2000 simulations, those cases where the demands were 600 to 900, in plan A, I had one large 900 plant, right? And that was able to service the demand. In this case, I have just 600 unit capacity plant. I am not able to serve the demand. So in those cases, plant A is able to sell 750 units, 800 units. I am only able to sell 600, plant B. That's why the differential between A and B is now getting bigger, right? Earlier the differential was 5.66, but now that I've started varying, right, the number of cases where A is better off than B are starting to increase, right? Because all those demand scenarios where there is overcapacity with regards to B, A is profiting, all right? So this is what is happening here. Now, if I look at this graph, okay, it essentially tells me the same thing. It tells me blue is A, maroon is B, all right? and A is better than B. The NPV of A is further on to the right, it's more positive, okay, and this is sort of the cumulative density function for A, for B, sorry, which is pink or maroon, whatever. But I can plot the same thing for A to see what kind of a curve A looks like, right? So what I'm going to do first is I want to take all of these values, all of these 2000 values, right, and convert them into 20 chunks, right? I want 20 sort of steps, or rather I want to take so I want to create 20 intervals, okay, so I can plot a curve, right? So I want to plot, I don't want to plot all of these 2000 points at one shot, I want to plot this interval. So what I'm going to do here is my bound, okay, is so I'm going to take 428 and 338 in this case, right, the minimum and maximum, right, and divide that range into 20 equal parts, right. So how do I do that? I say this is equal to, I take the minimum, right, and then I add, and then I say take the difference, this minus maximum minus minimum divided by 20, and I'm going to multiply it by this number, just so that it will keep increasing with equal steps, right. So I'll explain that again in 1 second. Oopsie, there we go. Oh, you know what I should have done? I should have, because now it's varying it every time. All right, so so look at this cell here, or look at these cells here. So in Excel, the dollar sign sort of means don't vary that cell, right? So normally when I take D3 and I drag it to the next row, D3 becomes E3, but when I say $D, $3, it doesn't vary, right? So let me do that again. So I don't want it to vary, right? Because I don't want it to randomly simulate every time. So we'll just sort of redo that. Let me get done with that. I'm going to say this is equal to, let me just put that in. Oops. All right, let's just copy this for now and then I'll explain again how it works. Right. Okay, so what have I done here? I've taken my upper and lower bounds, which in this case for me are 350 and 435. For you it will be a little bit different, but not hugely different, I would guess, right, roughly in the same ballpark. And I'm trying to divide that into 20 equal intervals, right. So there's one interval from 350 to 311, or minus 350 to minus 311, one interval from minus 311 to 271. Roughly the intervals are about 40 units apart, okay. And the reason I want to do it is I've got 2000 points. I want to see how they're distributed. I've got a minimum and I've got a maximum. Are they equally distributed, in which case I should get a nice sort of diagonal 45-degree line, right? Or are they bunched up towards the top and the bottom? Are they bunched up in the center? Where are these 2000 variables? Are these minimum and maximums outliers, right? So what am I doing? I'm taking that entire interval and I'm breaking it into 20 different pieces. How am I doing that? I'm taking the gap, I'm breaking it into 20 parts. So and then I'm starting from the lower bound, so 350 plus 20, 350 plus 2 into 20, 350 plus 3 into 20, or whatever it is, which is where this number comes in, right. So in the reason I multiply by F7, right, is because it multiplies by 1 into 20, 2 or 1 into 40, 2 into 40, 3 into 40, and there are incremental steps. Now, oops, yeah, every time I click it changes, but it's okay, it's roughly in the same ballpark. Now what I want to do is I want to see how many values occur in between 296 and minus 296 and minus 259. How many values occur in between minus 259 and minus 223? Okay. So for this there is a function here called countif, right. What this formula means is it says if the, what happened to my mouse? If the number is between B9 and B2008, right? If the numbers in those range are less than or equal to some parameter, then count it, right? So go through each of these, go through 85.38, 360.12, minus 45.68, etc. And if any of those numbers is less than whatever threshold, then count it, all right? So essentially what I'm going to do is, I'm going to copy this again. Oops, just going to copy this. right? So in other words, I'm asking, in the first instance, I was asking how many of the variables between B9 and B2008 were less than or equal to G7. G7 being 320.22. 320.22 is my minimum. It's the lowest value. So clearly there's only one less than or equal to that. Okay, but as I drag this down, when I go down one more, I'm asking how many values are less than minus 288.41, right? So there are more values, and this is cumulative, right? So I'm not looking at just that band. I'm looking at cumulatively under that band. Okay, and then finally I say how many values are less than 433, which is the outer end. So how many values are less than 433? All of them, right? All values are less than the maximum or less than or equal to the maximum. Only the minimum value is less than or equal to the minimum. So I've got 2000 on one side, 1 on the other. And then this tells me, gives me a little bit of a distribution. Okay, so far so good. So I've got one value in the first band, 5 of my 2000 values in the second band or in the first two bands, 17 in the first three bands, 35 in the first four bands, 70 in the first 5 bands, and so on, right? So when I start moving from my minimum possible NPV to my maximum possible NPV, I'm just counting, I'm splitting it into 20 equal intervals, and I'm counting how many are there cumulatively in the first interval, first 2 intervals, first 3 intervals, first 4 intervals, and when I look at all my 20 intervals, all my 2000 points are there, right? Any questions on this? And everyone's got something like this, okay? Now I'm just going to convert this into a percentage, right? Because 1, 5, 17, what does that mean, right? If I did 4000 simulations, I'd get more numbers, right? If I did 500 simulations, I'd get fewer numbers, right? So these numbers pertain to the number of simulations that we've done. And so what I'm going to do is I'm going to take this number and just going to divide it by 2000, which tells me the percentage of values, right, that are in that band or less than that band. Right, so 0.05 in the first band, and then when I go all the way down, 100% will. Okay. All I'm taking is, I'm just dividing the counts by 2000 because I get them as a percentage. I've got 2000 samples, right? So when I divide by 2000, I get a percentage, right? Because the number by itself is meaningless. Because I did 2000 simulations, I got 758, within the first 10 bands, right? If I had done 5000 simulations, I might have got 1680 within that band, whatever, right? So I want to sort of look at it as a percentage, right? So now I have the percentage of points in each band. Using this, I can actually now click on this graph and plot a graph, right? So I'm going to click on the graph, I'm going to right click, and go to select data. Already a bunch of data has been selected. There is NPVB, NPVA, NPVB mean, and I am going to add a series name which is NPVA. Okay. The series values are where did that go? Okay, let me add this again. Let's do NPVA. Okay, so where did it go? There we are. Sorry, yeah. So what I'm now going to plot is these boundaries. So I'm going to plot this boundary, which is the X series, and then the Y series is the percentage. Okay. Essentially all I'm sort of, again I'm dividing it into these intervals and I'm just plotting what percentage of my points are in each interval, right? So I get a little bit of a shape of the curve. Okay, I'm just plotting the cumulative distribution function. I've got 2000 values. How do those 2000 values look, right? And what I'm saying is those 2000 values are bunched between 329 and 434, and the blue, so 329 is somewhat here on the left, 434 is plus minus 329 is here, plus 434 is there, and this is how they sort of pan out. It looks a little bit like an S curve, right? And you can click a few enters here, there, etc. And you can see, you can do your F9s, I can't, but right, but you can see the curve move. Okay, roughly it will be about, it will be something like this. So the most of you get curves that look like this. The blue curve is a bit of an S curve, and the maroon curve is a bit almost like a straightish diagonal. Okay, what does that tell you? So first of all, whatever you do, and I encourage you to F9 as many times as you want, I doubt you'll ever get NPV-B to be greater than NPV-A, right? The dotted vertical lines are NPV-A and NPV-B, right? And NPV-A continues to be better than NPV-B, right? So that's one thing, okay? So even though we had this intuition at the start of the class that plan B was somehow better, right? We're not able to get, I mean, we've tried everything, right? We've tried randomizing demand, whatever, right? But A always seems to be better than B, right? Why is A better than B? Why is A better than B? And these curves give you a little bit of a hint as to why A is better than B. What's the difference between the two curves? Right, so what can you say about the range of values that you find with A and B? Which one takes a larger range of values, which one takes a smaller range of values? So A takes a larger range of values, B caps its upside, and particularly, so B caps its downside but also particularly its upside, right? B is not able to gain more profitability, right? Because essentially, unfortunately, sometimes the demand is greater than what B can supply. A, because it's a bit unrestricted, right? In some cases, you get cases where demand is exactly 150, 300 and 450, right? Is one worst case scenario, right? It's always at the lower end, 150, 300 and 450, in which case you're probably losing a lot of money out of A. That's why A's negative is much higher, right? When you look at the minimum values, right? When you look at the minimum values on the top left of the screen now, A's minimum is always worse than B's minimum, right? But A's maximum is often higher than B's maximum, right? And what's unfortunately happening with B is, although on the downside its losses are getting cut, right? Because in the worst case scenarios, you're investing slowly. In the best case scenarios, you're just not able to bring back those profits, right? This is exactly the hotel room analogy. In the worst case scenario, I'm losing money, right? In the best case scenario, I'm not able to gain that money back, right? Because my capacity is capped. A has larger capacity, so while it's losing money, it's also able to gain back money, right? So very counterintuitively, right, A seems to be the better bet, okay? But does that feel right? The one monolithic plant seems to be better, whether it's static or dynamic analysis, than the modular plant. Does that instinctively feel right? I bet you wouldn't see that much of a change, because the same dynamic exists. If you reduce demand variation to 0, okay, A is still up by 5.66, and the more you increase the demand variation, the gap between A and B is increasing. So it doesn't matter, 40%, yes, you might not get this big a spread, but A is still going to be better than B. For who? So you're saying A, people may not be but you know, if I were to make a decision today based on this, what would I take? Right? If I showed you all this analysis, right, you're going to have to say A. I mean, it's more investment, but it clearly shows you that you're going to be more profitable, right, than if you did B. Yeah. NPV in case A. Why do you say that? The mean NPV is 105. The highest value is 427, that's fine. But when I look at the mean, right, A is still better than B. Right? And when I look at, okay, so up until this point here, where the curves cross, okay, B is better than A, right? It's only after the curves cross that A is starting to get better than B, if you will, right? So, but the, anyway, this is a cumulative probability distribution, so you can't really read too much into it. But there seem to be, so there's a 30% probability, right? In 30% of your cases, A is better than, B is better than A. Right? In 30% of your cases, B seems to be better than A. Right? In most other cases, A seems to be better than B, and overall A is better than B. Okay, so the question is, are you missing something? Or is it counterintuitive? Do you all agree? Always invest in large plants. So build 500 MLD desal plants. Do not build modularized desal plants. Build large airports. Do not build modular stuff. Right? Do we agree? That should be the strategy. Okay, instinctively that doesn't feel right, right? Okay, yet the data is showing that this is true. Okay, there are some assumptions, maybe the costs are a bit different, etc. But roughly this is how things are. Larger plants tend to have lower variable costs. Okay, remember plan B also has salvage value, which plant A doesn't have. So there is some advantage already I've put in. Okay, what's the one thing that we haven't changed? Why are we building modular? What's the point of building modular? Huh? What can you do if you build modular? You can change your plans to do what? What plans can you change? You can change your plans to invest, right, in the future. Okay. Now let's go back to plan B, to plan A. What is my investment plan? Tell me from this spreadsheet, what is my investment plan? What is my investment plan here? What's the strategy? What am I doing? I am investing 900, that one plant in year 0 and going through. Alright, that's my investment plan. Let me go to plan B. What's my investment plan here? Build one every year. Okay. Now based on what Jayakishan was saying, what can I do? Can I change anything to plan A? Right, I need to build the plant. If I don't build the plant, I get nothing, right? So I'm going to build the plant. Can I change something to plan B? What could I change? So I could invest 600, right? Or what else could I do? What else could I do? So one option is at the end of the second year, go to 600. What else could I do? So don't build at all in the second year, right, is another option, right? So in other words, the whole point of building the modular plant was it gives me an option to build or not to build. Is that option being modeled here? Right? Is there an option? No, it's fixed. Whether you like it or not, build 300 first year, build 300 second year, build 300 third year. Right, but now I actually have an option of building. Okay, so now let's see what happens. Right, if I start, so when would I put in this option? Right, what would my logic be? I have an option of building or not building. Let's assume that I can't go from 300 to 600. Right, let's just assume. No, I mean that's also an option. Okay, how would I decide? So in the first year I have to build one. Okay, that's a given. Right, I start off. What should my decision be in the second year? How should I make a decision? So, well, the demand risk I know is 50%. Okay, how would I make a decision? Give me a simple rule.
Like when you get some other deal where you can invest this money.
No. So in this project, okay, I am ready to invest 1, 2, and 3. Okay, but I don't have to invest 1, 2, 3. All right. In the beginning, I invest 1 because I'm getting into the project. Okay. At the end of the first year, how do I decide whether to do 2 or 3 or stay with 1? But if I do the MARR, or if I do the rate of return, A is better than B. See, as it is, by investing, by delaying my investment itself, A is better than B. Alright, if I, instead of building 2, I build 3 right away and put in more costs earlier, A is going to continue to be better than B. Okay, but how do I exercise, what is the logic that we should have? What will I do with demand after first year? So one way of looking at it is, I sort of look at, I don't look at MAR or whatever, I say, look, I look at the demand after first year. If the demand after first year was good, I build a plant. If the demand after first year was not good, I don't build a plant. Alright, so now, because this is the whole point of that flexibility, the whole point of plant B is I now have that ability to build or not to build. Alright, so now let's just close this spreadsheet and open 4. Don't open 3, 3 is not required. Open 4-1. Okay, let me know if you guys have all opened 4-1. You guys have all opened 4-1? Alright, now 4-1 is exactly the same, except that in all my earlier spreadsheets, right, the number of plants was 1, 2 and 3. Okay, here I've said 1 because obviously I'm assuming I'm getting into the project, I'm building 1, but in year 2 and year 3 I've not put anything else, right. So I'm going to put a very simple decision making rule, right. I'm going to say, right, if, I've got to put the equal to because it's logical, if the demand in the last year, if the demand in year 1, right, is greater than the capacity in year 1, right, if the demand in year 1 is greater than the capacity in year 1, right, then I take the number of plants I had in year 1 and I add 1. Okay, if E5 is greater than E4, E5 is demand, E4 is production. So if E5 is greater than E4, right, then I will increase by 1. Okay, otherwise I won't increase. It will just be the same value as the previous year. Right, that's what's there at the bottom, that formula there. Oh, again I have to, sorry, increase the font. Right. Okay, so I've taken this formula here. What does it say? If the demand exceeded capacity last year, then invest. Right. If the demand did not exceed capacity last year, then don't invest. Okay, same thing here, except I am now looking at year 2. So I'm going to say if the demand exceeded capacity, then take whatever I had last year and increase it by 1, else just keep what I had last year. Will be the addition of what? Will be, I'm adding 1, right? So here I'm saying take previous last year's demand versus supply, right? If the demand was greater than supply, right, then add 1 more. If the demand was not greater than supply, then don't add. Right? So I'm looking at scenarios where the demand is not picking up and I'm saying don't add. Alright, so very simple formula. Alright, it's the same thing here, E5 greater than, you can cut and paste this, except when you do year 3, E's will be replaced by G's. Right, E's become replaced by G's. Okay, if you've done this, then click on simulation. Click on simulation and tell me what you see. What do you see? Now all of a sudden B is better than A, right? Because now you have exercised that fundamental flexibility which we all intuitively thought made B superior to A, which is, look, if demand isn't picking up, don't throw your money into that project, right? So there is, for instance, a scenario where you know, you might, so you can easily, in many scenarios, you can go 1, 1, 2. There is actually a scenario where you can go 1, 1, 1. Okay, so in the first scenario, right, it was less than 300. Okay, then you would not invest. In the second scenario, when the demand was exactly 300, you might still not invest, right? And therefore, you are minimizing your outlay, right, instead of committing yourself to 1, 2, 3, right? So the whole point of flexibility is you can make a decision to invest or not invest. Plant A is not flexible. You're putting in the 900, demand is varying, and you get an NPV of whatever it is, right? You get a mean NPV of about 100. Okay, if you use the same logic with plant B, because the operating costs of plant A are lower, you know, A is better, right? If you use the same fixed logic, right, there's no flexibility, I'm going to do 1, 2, 3. Okay, A is obviously going to be better because its operating costs, its variable costs are lower. But when you bring in the flexibility of B, which says I don't need to invest when I don't need to, right? So here what's happening is, if demand goes through the roof, if demand at the end of year 3 is 1,300, there's nothing I can do about it. Whether it's A or B, I'll only sell 900, right? It's like the hotel room thing, okay? But if demand is low, don't go ahead and build the next 50 rooms in your hotel right away, right? Why are you building 100 rooms and then saying I have only 40% occupancy, right? Build as demand develops, right? So this is one kind of flexibility. This is also, we talked about the parking garage example in class, right? So you build 3 stories, then when demand picks up, build 4, build 5, build 6, right, you know, or whatever you want. But don't necessarily build 6 and then just hope that demand will pick up. So there are 3 options. One is you build 6 and you're taking a gamble. The other is you say, I'll build 3 today, but I'm committed to building 4 next year, 5 the year after, 6 the year after, right? Where again, you're incurring extra costs for the reconstruction and you may not get the benefits. The third is the option, is the flexibility, right? Where you're saying, I'm actually going to build only when demand exists. So that extra capital investment will get an immediate return, right? And if the demand is low, I will not waste extra money on capital investment, right? So that essentially is flexibility. The ability to choose, in this case, when to invest. There's one kind of flexibility, right? In this case, it's the flexibility to expand your production, many other kinds of flexibilities. But if you model the flexibility, then you see that the flexible option is often better than the inflexible option, and in this case the differential is about $50,000 or whatever the units were, right? So this essentially in a nutshell is how flexibility is modeled, okay, and how you can actually see if flexibility gives you benefits, right? And it's very clear that because of this sort of law of averages kind of reasoning, inflexible projects, if you assume inflexibility, and this is what most consultants do, by the way, you assume inflexibility when you do your modeling, right? You get a certain response. If you start assuming randomness, you start doing Monte Carlo simulations, right, and you start putting in flexibility to combat that randomness, then you find you get much higher NPVs. Recall, the NPV of A has not changed, it's been hovering around 100, right? The NPV of B has gone from 60 to 165, right? 2.5 times, whatever. Right? So this is how this is modeled, and so therefore when we do these analysis for infrastructure projects, right, we should try to see if we can do this kind of Monte Carlo simulation plus flexibility modeling, right, to really see, look, I can put in a number of options, you can use the same concept, I can put in a number of different options, right, and then I can evaluate which option is actually giving me a large amount of value, therefore what option should I design into the project, right. So you can do a lot of analysis to understand how the project should be designed, okay, because this is just one option. Yeah. So that might be, yeah, there's a little bit of the salvage value, you know, discussion, because yeah, that I think is, yeah, so you should be salvage value per plant and then we should have that accordingly. But again, my guess is you're getting salvage value in the 3rd year, it's being discounted, you know, 3 years. So I think your effects of that are, I mean, it's true, it will have some effects, and there will be certain cases where the effects are magnified. But yeah, I agree with you. There's a little bit of a flaw in this, but I doubt it will change the results completely. I think you will find that maybe the gap narrows a little bit. Okay, but that's a very good observation. Okay. So do you guys get how you model flexibility and why flexibility is valuable? Right? If you went and took up a job with someone next year and they asked you to do a demand analysis on a road, would you feel comfortable being able to do this kind of analysis? If some consultant gave you traffic data, right, and he says, I did traffic surveys for whatever a number of days and this is what I found. Okay, could you then, do you feel you will be able to do this kind of analysis? Right? I mean, obviously you may not be able to do it right away because you're not familiar with some of these, but conceptually, right, you guys clear how this kind of analysis could be done? Because this is exactly, I mean, road projects, this could for instance be how you decide how to go from a 4-lane to a 6-lane road. Right? So somebody says build a 6-lane road and you say, why am I building a 6-lane road? Let me build a 4-lane road and then decide later on when I should expand to 6-lane. Right? So based on my traffic studies and my uncertainty around traffic, I can do some simulations and figure out what is the value of being given the option to expand later, and also roughly from these simulations, roughly at what point does that kick in? Right? When do these demand values roughly, get to a point? So I can also plan my investment. Right? I can sort of say, okay, I'm investing now and then 6 or 7 years later I'm going to invest in the expansion, and you will have a far better competitive advantage over your competitors who budget for that expansion right away. Right? And of course there are other kinds of trends, and I'll show you, there's a PowerPoint that I have, I won't run through it, but I'll show you, there are all kinds of ways in which, so you can look at demand progression. So we looked at a very simple distribution like 50% whatever, but you can also have distributions that say the next year's demand is last year's demand plus some variation. So you have formulae that come out of geometric Brownian motion that look at this thing. There's a little bit of a trend. So I can see a 2% increase every year, but it's not constant 2%. There's some uncertainty around that trend, right? So you can start putting in formulae that start modeling demand in a little bit more sophisticated manner, right? It doesn't have to be 300, 600, 900. From that you do some variation. You can take last year's demand. You can say this is a bit of a trend. This is some uncertainty surrounding that trend. It might go down, it might go up, etc. And these people use, by the way, to simulate stock prices and so on. There's also reversion to the mean, which means you have this sort of iterative motion where there is constant fluctuation around a mean. That might be another sort of formula. Then there's sort of the S curve. You might have demand that goes on some kind of an S curve where there's a little bit of saturation, right? Which means you actually have two parts. There's a growing part with a certain equation and a saturation part. So if you're selling a product, it's stupid to sort of expect that people will continue to keep buying that product, right? Because over a period of time, people might already have it, and some of these products don't get replaced that quickly, right? Which means you have a growth curve and a saturation curve. So the way you model demand, we modeled it very simply. We took 300, 600, 900 and varied a little bit around it. There are many ways in which you can model demand for roads or for televisions or whatever in a much more sophisticated manner, but the principle is the same. Demand is varying, so I need to do a Monte Carlo kind of simulation because I have to average out a number of data points because there is variability. And if I can put in flexibility where some input parameters, some investment parameters can be staggered based on my discretion, right? And that's the key part. It's staggered based on my discretion. When I did 1, 2, 3, I had no discretion. It was being done irrespective whether I liked it or not. But when I can actually stagger at my discretion, that means I have an option, right, to do something. Then what would the returns increase in NPV be, right? Certain options returns in NPV might be negligible, right? There may be no return on NPV. Other options, they might be much larger NPVs. And then you can take that back to the person who's awarding the project and say this flexibility should be put in because it increases project value. So allow the developer to go from 2 lanes to 4 lanes or 4 lanes to 6 lanes at their discretion, right? Or you might put in the higher cost of acquiring land later on, and you might say, boss, might just better off to do 2 lanes to 6 lanes today, right? Because if you want to do a little bit of land acquisition and then 5 years from now do more land acquisition, it will never get done. So you can weight these flexibilities. Some might work, some might not. But this is really the way in which you analyze projects to determine, A, is the project feasible, and what kinds of flexibilities do I put in to make the project feasible. Yeah? Cool. So, comfortable, conceptually comfortable, at least, okay, good.